Hi, everyone. My name is Mike Valley, and on behalf of the Applied Technology Council, I'd like to welcome you to this webinar on the Unreinforced Masonry Recommendations in FEMA P-2208, NEHRP Recommended Revisions to ASCE 4117. This webinar is brought to you by the Applied Technology Council under a FEMA NEHRP Architect Engineer contract. If you haven't already, you can download the handouts using the link in the chat. We know that many of you are interested in receiving professional development hours for your attendance today. For those who registered and attend the webinar, a certificate documenting the professional development hours will be sent by email within 4 weeks. If at any time during the webinar you have questions, please type them into the Q&A window that you can open from the Zoom control panel. We're planning to have a live question and answer session at the end of the webinar. We'll be answering questions that were typed into that panel. Please submit your questions as you have them rather than waiting until the end of the webinar. If there are questions we're not able to answer live, we plan to provide written responses for as many as practically feasible. Our project sponsor, Christina Aronson, who is with FEMA's Earthquake and Wind Programs branch, is unable to join us today. She, like most of FEMA's staff, is currently deployed to help with disasters. So I'll read the introductory comments that she prepared. Hello, my name is Christina Aronson, and I am a structural engineer at the Federal Emergency Management Agency's National Earthquake Hazard Reduction Program, FEMA NEHRP. It's my pleasure to welcome you to today's webinar, the second of 3, covering NEHRP Recommended Revisions to ASCE 4117, Seismic Evaluation and Retrofit of Existing Buildings, FEMA P-2208. Today we'll be covering the background and studies of P-2208's recommended revisions to unreinforced masonry portions of ASCE 4117. Just to set the stage, FEMA has the goal of reducing the ever-increasing cost that disasters inflict on our country. Addressing the risk presented by our population of existing buildings, of course, is the most effective way of reducing the future cost of disasters. The National Earthquake Hazard Reduction Program, NEHRP, is composed of 4 agencies: NIST, USGS, NSF, and FEMA. As part of its statutory responsibilities under NEHRP, FEMA is charged with supporting the investigation of seismic technical design issues, the development, publication, and dissemination of technical design and construction guidance products, and support of model codes that are cost-effective and affordable. This report documents the work of a 5-year FEMA NEHRP project. FEMA submitted 35 detailed proposed revisions into the official ASCE 41 consensus standards process. FEMA P-2208 presents the submitted change proposals and commentary in addition to the results from the technical studies that informed the proposals. It's not intended to replace ASCE 41. FEMA values this partnership with the American Society of Civil Engineers and the important work it does to provide national consensus engineering standards for buildings. We hope you find this webinar useful, and we encourage you to let us know if you have any questions. We also want to thank the Applied Technology Council for managing this project and helping deliver this session under a FEMA NEHRP Architect Engineer contract. Additionally, we thank Rebecca Collins for presenting here. She has been a tireless worker on this effort. The names and affiliations of all who contributed to this work are provided in the report. Without their dedication and hard work, this publication would not have been possible. The nation is safer from the next earthquake as a result. So those were Christina's comments. We thank her. We're sorry that she can't be here. We're glad that she's helping out others, though, in her deployment. So now let me tell you just a little bit about the presenter that we have today. Our presenter, Rebecca Hicks Collins, is a senior structural project manager at Coghlan Porter Lundin. Rebecca has advanced technical expertise, fills leadership roles on committees that help shape code development, and provide significant internal mentorship to project managers and engineers. She specializes in seismic upgrades and has an extensive URM retrofit resume. At the forefront of her field, she served on the ASCE 4123 subcommittees for analysis and for general requirements, and on the team that prepared the FEMA P-2208 recommendations related to unreinforced masonry that she will present today. So now we'll turn it to you, Rebecca.
Thank you, Mike. And welcome everyone to the NEHRP Recommended Revisions for Unreinforced Masonry Provisions. We hope this webinar on technical background will aid you in your practice of evaluating and retrofitting unreinforced masonry buildings. So our agenda today, we're going to go through some background on where this is all coming from. We'll walk through the proposed changes, and this all mirrors what's in the document FEMA P-2208. So you can read in even more detail there. And then at the end, we'll take questions. So ASCE 4117 is the standard for seismic evaluation and retrofit of existing buildings. It's a consensus-based standards, so it follows ANSI guidelines. Members vote on all the provisions. All comments must be resolved from members, and there's a public balloting process. So all these committee members are volunteers and donate their time. And while all these people contribute many hours, there's a limit on what volunteers can produce. So the ATC 140 project is FEMA funded to investigate and address these technical issues and develop guidance regarding the seismic evaluation to help feed into the ASCE 41 committee. So we generated this report, FEMA P-2208. It has recommended revisions with actual underline and strikeout on the ASCE 41 text, and it also includes the background technical studies on why we recommend these changes. All of these changes were then presented to the ASCE 4123 committee, and then the committee took these proposals, they modified them as they saw fit through the process, and they were placed then into the standard. So ATC 140 is a 5-year project funded by FEMA. The ATC team was led by John Heitz. There's a project technical committee led by Terry Lundeen. And these project technical committee provided input on what we should study and guidance and expertise on recommendations. And some of them were also members of the various working groups. And without all of the members' help, this project would not have been possible. There were 6 working groups that generated 35 change proposals for ASCE 41, including the technical background for those changes. All of these changes were accepted by ASCE 4123, and now FEMA is funding presentations on the technical background for 3 of these sections. The nonlinear analysis one has already taken place, and the recording is available from ATC. Concrete structural walls is coming up in a couple weeks. And today we're doing unreinforced masonry. This slide shows the first 5 pages of ASCE 4123, which is a summary of all the changes made in the document. And about half of the major changes in ASCE 41 began with material provided by this ATC 140 project. So this FEMA funding has made a huge difference in getting the standard updated. The recommendations of FEMA P-2208 were modified by ASCE 41 committees. So the document contains the technical background, but not the final standard language. So it's something to be aware of. You can't just take the FEMA P-2208 language verbatim, because it might have been changed a bit. So it's intended to be used in conjunction with ASCE 41. And we're presenting the recommended revisions that came out of this particular project, but it's just the technical background, not how to use the document. For the final changes, ASCE intends to present webinars on the various topics, and these webinars can be purchased and viewed on their continuing education page. So that's where you would go for exactly how to implement ASCE 41. FEMA is also going to update P-2006. This was the design examples for ASCE 4113, and now it will be updated to cover ASCE 4123. And that document's expected to be released in late 2025. Work's already underway on it. I'd like to acknowledge the contributions of the ATC Masonry team members. We could not have done these updates without all their expertise and knowledge. And the motivation for updating this standard is the seismic risk from existing buildings is very high, especially those that were constructed prior to the development and adoption of modern building codes. For masonry in particular, the majority of the ASCE 4117 goes back to FEMA 273, which was published in 1997. And that goes back even further to the ABK method developed in the 1980s. So a lot of this hasn't been updated in a while. Chapter 11 has had some sections updated more recently, mainly spandrels and the wall failure modes. But the further research that has been done since that time and use of the updated provisions has led to a desire for more changes. And just so to make sure everybody's aware on unreinforced masonry, it occurs in two places in ASCE 41. There's chapter 11, which may be used for any performance objective and works with the main body of the document. So 11 just covers masonry, and for your demands, you'd go to the analysis, chapter 7, and you'd work it in conjunction with all the other sections. Whereas the chapter 16 part of unreinforced masonry is just the special procedure. It's a limited performance objective, and it's really meant to be more standalone. So chapter 16 evaluations identify the major flaws in the URM buildings, but typically at a lower seismic hazard level. Chapter 16 is also limited to certain building types. For example, they have to have flexible diaphragms, they have to be 6 stories or less, and there's other requirements in there. So the items discussed today in this presentation, we'll try and clarify which chapter they're applicable to, because they're not just mix and match. So starting off with new vertical elements in chapter 16. So the URM special procedure in chapter 16 has always done the evaluation of URM buildings, but it didn't have clear provisions for retrofit of those. ASCE 4117 added some retrofit provisions, but they actually stepped outside the special procedure, mixing and matching between the main body, go get your demands from chapter 7, and then trying to come back to the special procedure. This was a bit confusing, and it also made retrofits more conservative than the rest of chapter 16 evaluations, because you were going back to that main body with a different performance objective, potentially. Another issue is deformation compatibility. New elements are often not stiff enough to attract loads away from the URM before it fails. So we wanted to address that. There was also no clear path for distributing shear between new and existing elements. And detailing requirements for new elements were never mentioned in the special procedure. So the goal of our working group was to create an integrated set of provisions for new vertical elements going into a URM building that deals with demands, drifts, and detailing. So 3 different case study models were developed. We started with this 2-story model with lots of openings, and then we stretched it up to 6 stories or collapsed it down to 1 stories, keeping the same footprint and opening distribution, just to see what would happen with different variables. We also looked at 3 different retrofit scenarios. We studied the transverse direction, as that was the direction the building had the most issues. We did situation 1 here, where we added shotcrete on both ends at the front and rear elevations. Another retrofit option we studied was if you put an element in the middle of the building, either a reinforced concrete shear wall or a steel moment frame, and this would then take some of the seismic load and reduce the burden on the 2 end walls. And then situation 3 was where we studied an open front building. These are very common, especially along main streets where you'll have retail at the first floor. Here in Seattle, we often find it's just cast iron columns, no masonry, no moment frame, and something needs to be done to strengthen the building there. And we studied both steel chevron brace frames and steel moment frames. Now, not all these retrofits were applied to all the different combinations, but we did study quite a few. So in this particular one, we had a new element that was applied, new concrete shear wall added along 1 elevation. It was only done at the first floor because the upper floor demands were okay. And we compared it to the unretrofitted condition using the demands based on the special procedure, Chapter 16. We also looked at it with demands based on Chapter 11 with and without M factors. So basically we tried, okay, if we were going to design this new element, let's try all the different possible methods we can think of and see what the results were. And what we found was using Chapter 11 was really difficult, as determining an M factor wasn't simple. The concrete and the masonry are now attached, so it's not obvious how they would interact. Do you use an M factor for concrete? Do you use an M factor for masonry? Is it somewhere in between? Based on past studies with FEMA 547 and FEMA P-2208 and this current study, we decided to recommend to make it clear that new elements may use demands based on the special procedure. So essentially, we're getting a retrofit behavior that's consistent with the special procedure goals. So using that special procedure then, that means you would use the same equation that you were using already to calculate your loads on your URM walls. And in this particular example, you'd calculate your roof load, wouldn't change because you haven't changed your weights, you haven't changed your diaphragm weight or capacity. And then you get to the second floor, you would have an increase in load because you would include that wall weight. And then summing up the roof and second floor would give you the demand on the combined wall, existing wall plus URM. So that would give you your demand. And then once the wall force is calculated, the recommended revision clarifies that the shear distribution should be based on relative rigidities. So your URM wall stiffness and concrete wall stiffness would be calculated, and then you proportion your demand based on those stiffnesses. Each wall only needs to be checked for that portion. Also, you do need to check the URM, even if you decide to say, well, I'll just design my concrete wall for 100% of the forces. It's still a requirement to check the URM wall and make sure that it is not going to fall apart. So the impact of this change is you're going to have reduced demands compared to what we had in 4117, because you're not stepping outside the special procedure and using the Chapter 7 analysis, because the special procedure forces are lower. And an engineer may still conservatively design the new concrete wall for 100% of the forces, but you are going to have to check the URM on it. Now, sometimes you try to design your concrete wall, or maybe it's a steel moment frame or brace frame, and you find that you get ridiculously large sizes in order to protect your URM wall. So we did add commentary to help address that, saying that if you want to design your new elements for 100% of the load and not check the URM walls, you can, but then you have to provide complete gravity support for your floor and roof framing. And you have to have vertical bracing of the URM walls to prevent them from becoming falling hazards. So they'd have to be tied back into whatever you're doing. So essentially your URM wall just became very thick cladding. So that is still allowed if you start to get ridiculously large sizes for your new elements. So for drifts, we studied reinforced concrete shear walls and moment frames placed at midspan of the diaphragm to see what this was doing to our diaphragm and to the two end walls. So currently ASCE 4117 has a 0.75 drift limit, but only for moment frames, and it's actually at a different force level because it was stepping outside the special procedure. So we took a look at, well, what if we have all these different drift limits from none on down to 0.75% were studied. And what we found is that at the very high limit or no drift limit, the steel moment frames tended to produce about the same midspan diaphragm drift as an unretrofitted building. So in other words, the steel moment frame isn't actually pulling load away from the two end walls effectively. It really took until you got down to the 0.75 drift limit to cut the mid-span diaphragm drifts in half. So that was going to be where the recommendation was leading. We did design these frames with a 2D program because we want to try and make sure this is easy for engineers. If you want to go in and design a new element, it's flexible diaphragms, URM building, you could use a 2D program. So we did that initially, and then we checked it with the 3D program and found that the answers were acceptable. Another thing that we found as we were looking at diaphragm drifts was what your diaphragm span was. And currently the diaphragm span, the way it's defined, is between URM walls. And we realized that that shouldn't actually be correct. We really should revise the language to say that the diaphragm span should be between vertical elements. So if you add a new element in with that maximum drift of 0.75, you could then reduce your diaphragm span and come in here. So that's going to be another recommendation we have. With the open front building, when we studied it, we also did similar studies with various drift limits, including that 0.75% drift limit. And again, found that that's really where we needed to be to help protect the URM. We also, again, did 2D models and checked it with 3D and found that 2D were acceptable. So all of these revisions are going to result in 0.75 drift limit retained for new moment frames, and it's now expanded to all new vertical elements. This was really necessary in order to reduce the diaphragm drifts and limit the tributary loads to the existing URM walls. But this time, at least, we will be staying within the special procedure, so you will be using lower loads than you would have been if you had stepped out and went back to Chapter 7. Additionally, the commentary does clarify you can just use a simple 2D model because we really want to make the modeling easier for practicing engineers. And then this is the other change we recommended, saying the diaphragm span is between vertical elements. We also looked at detailing for new elements. Once you start using that 0.75 drift limit, this really leads to members that are much larger than needed for just the force demands. So the highest demand to capacity ratio we had was around 0.5. So there's a good amount of overstrength in this system now. And you only need limited ductility from your new elements. So this led to the question of, do we really need to say we have to have special systems? Do we need a special moment frame, or would an ordinary moment frame or ordinary concrete shear wall be acceptable? So we did go through and do a review of what the ordinary requirements are. So for a steel ordinary concentrically braced frame, the braces, you can actually allow tension-only members. They only need to be moderately ductile. And then for your brace connections, you design them for basically the member strength and with some overstrength factor when you're looking at new design. So this is all the requirements there are. Whereas if you look at a special system, you've got a much longer list that needs to be met. Similar for ordinary moment frames, you don't need special B over T ratios, no protected zones, just the higher design on connections to make sure they're stronger than the members. And for ordinary concrete shear walls, Chapter 18 doesn't even have any detailing requirements for them. You would just default to the Chapter 11 in ACI 318 that has some minimum reinforcement ratios, minimum bar spacing. As a matter of fact, we were a little surprised to see that it didn't even require you had hooks on your horizontal bars at wall ends. So the recommendations we made were that an ordinary system is acceptable since we only need limited ductility. One exception was we did decide to say that reinforced concrete shear walls, you do need a 90-degree hook on the ends. It's a limited edition, not a lot of expense, and it'll still give you better behavior. The other thing we looked at was to make sure that certain systems that are not permitted in seismic design category C in ASCE 7 are also not allowed for vertical elements in regions of high seismicity in 41.7 and 41.23. Basically, the systems this eliminates are your unreinforced concrete shear walls, unreinforced masonry shear walls, you can't add new ones, or reinforced concrete moment frames, the ordinary ones. So these are systems that aren't usually used anyway in areas of high seismicity, so we're not really changing what engineers are doing most likely in their designs. So that was the vertical elements. Now looking at subdiaphragms in Chapter 16. The special procedure in 4117 requires that you anchor the walls, the URM wall, to the diaphragm. This, as everybody who's looked at URM knows, is one of the biggest things we can do to help prevent failures on these buildings. However, it doesn't explicitly require developing that load into the diaphragm. You can just provide an anchor from the wall and connect it to the first joist bay, and that would meet the provisions in 4117, Chapter 16. Without this additional strapping and blocking, though, you could actually end up with the floor fracturing at this first joist bay. And we don't want that behavior. So this is different from the main procedure in 4117, which does require that the wall anchorage be developed back into the diaphragm. But since the special procedure is standalone, it doesn't reference back to that piece. So our proposal was to develop the anchorage. Basically, we mirrored the requirements back in the main procedure of 4117 using subdiaphragms. So this does require that you'd have to calculate subdiaphragms, cross ties, and chords. So that's one path, but we also wanted to consider a simpler path since this is the special procedure. It's a limited performance objective. The intent is to encourage and not discourage an owner to undertake these retrofits. So in addition, wood diaphragms also behave in a ductile manner, and they potentially have greater capacities than the prescriptive calculations. So as an alternate, simpler method that we studied, we started with an example building and we looked at full code. So over here on the left, this is what you'd have to do. Calculate your subdiaphragms, your cross ties, all the way across the building. We also looked at a partial code method. What if you just develop your anchor 10 feet or maybe 8 feet back into the diaphragm, and you don't do the cross ties and you don't do the subdiaphragm calculations? We studied this for both transverse and longitudinal directions. I'm just showing the picture for transverse here. And when we looked at the subdiaphragm forces, if no cross ties were added and did the calculations and compared them, we also looked at what would happen with the different diaphragm types. So if you don't have subdiaphragm chords or cross ties, you still have a diaphragm that continues across those boundaries and could potentially develop forces. So we did free body diagrams of the framing and evaluated our different wood diaphragm options. So as an example, here's diagonal sheathing in the transverse direction. We assumed minimum nailing, strength of connections. We really looked at the board splices because that was going to be our weakest point. And we found that the diaphragms had larger capacities than expected, except for single straight sheathing. There, at that point, you reach a point where there's no load path. So then we combined our building case studies and our diaphragm studies into a giant parametric study where we changed building size, diaphragm aspect ratios, looked at solid walls with openings, different diaphragm capacities, and different development lengths. And for typical building sizes, and using Chapter 16 diaphragm capacities, not our larger ones that we did with those studies, we were getting DCRs under 2.5. We did end up having to exclude single diagonal sheath. The DCRs jumped up way too high on that one. So we ended up saying we're going to need to exclude that because the DCRs were too high. So based on all those studies, there's also a simplified path compared to a full subdiaphragm analysis that takes advantage of these more ductile wood diaphragms. So you only need to develop your anchorage a minimum of 8 feet into the diaphragm. So going back to our wall anchorage figure, if no subdiaphragm analysis was performed, you could come in and say, we're going to develop it back 8 feet. This is showing joist parallel. You could also, the joists are perpendicular. you could attach your anchor to the joist. And if your joist is longer than 8 feet, then you would be done. You wouldn't have to remove finishes and come back going further into the building. So the impacts of this revision are we can get better URM performance because our anchors are now developed. We're requiring that. But we're allowing multiple methods to meet the requirements. You can do a full analysis, or you can come in and do something quicker and just say 8 feet. We'll make sure and meet that. For wall out of plane behavior, we looked at this for both chapters 11 and 16. And in chapter 11, we're still using this table for collapse prevention for H/T ratios on the URM walls. And it's based on older research, and that research at the time stopped at about 0.4 G. But we now have many areas in the country with much higher spectral acceleration values. Chapter 11 did include an updated H/T ratio out of plane check for life safety that was based on Penner and Elwood method. And we'd like to bring the different performance levels all into one standard system, not some equation, some table. We also want to address what to do for limited safety and damage control performance levels because they weren't addressed. And this method, equation method that's in there, the Penner and Elwood method, has a bunch of different variables. Depends on diaphragm stiffness, axial load on the walls, wall thickness, and performance level. And Penner and Elwood included these variables. They do note that there are a lot more variables that would still need to be tested, and they recommended a bunch of future studies. So hopefully someday we'll get that, and maybe we can incorporate more items into this. We did parametric studies again with this equation for a bunch of different wall types. This is an example of just one wall type. This is the all other walls. So it's not a first floor wall. It's not a top floor wall, and it's not in a one-story building. And along here at the bottom axis, you have your H/T ratios, and along the left, you have your SX1. And so you can see if you come in at 0.4, the H/T ratio previously, that's the stair-steppy line, it was 13. But when you run through the equations with the Penner and Elwood method with a bunch of different walls, what you find is that that original stair step over in the range where it was operating below 0.4 is actually conservative. It's following the most conservative line. And then once you get past 0.4 G, it quickly becomes very unconservative. So if you are in Seattle, which is this flat line here, and you're looking at BSE 2E, the Penner and Elwood method would say you probably need to brace your wall unless you happen to have a lot of gravity. And whereas the past method was allowing an H/T up to 13, which is rather unconservative. This upper line is for San Francisco. So you can see that with the new equation method, you're going to be bracing almost all of your walls because the H/T ratio is not going to be adequate. We also looked at including cross walls, which is not currently in the Penner and Elwood method or the equations. Cross walls as a means of decreasing diaphragm amplification and acting as dampers for flexible wood systems had been included previously in those tables and charts that had been developed back in the 1980s. So we came up with a cross wall factor. We used 20% damping. It's a little conservative. Our literature review had found you could probably get 25%. But this adding another factor into it would allow us to increase the damping. Well, the damping's already there from the cross. So it would allow us to increase our H/T ratios up to 25%. So the result of this studies is we ended up with new factors for not just life safety, that was in there previously for the equation, but now we have factors for the other performance level methods. We get a little bit of a benefit from stiff diaphragms, so we're going to keep that in for collapse prevention. And we also added the new crosswall factor to the equation. The old collapse prevention table of H/T ratios will be deleted from the standard. So the impact of this is going to be at those higher seismicities, the Seattle and San Francisco, but other areas also. Your H/T ratios are going to be much lower. So more walls are going to require strong backing and high seismicities. That was for Chapter 11. We then did a similar set of studies for Chapter 16, the special procedure, because it currently also has a table that again only goes up to 0.4 G. So similar example, this stair step line is what the current ASCE 4117 table does. And we are recommending that the table, again, stair step up for some higher seismicities to account for this lower line along here. We do stop at an H/T of 8 based on past review of building behavior. We found that once you hit an H/T 8, the walls are acceptable. So it's not really an issue at that point. So this would be then the proposed revisions to the Chapter 16 table. You can see it's expanded out with a few more columns. We still have benefits for cross walls. That's this column A. So you can still get some benefit there. Also, we are going to allow the user to use the Chapter 11 equations. So you can go through and calculate an H/T ratio if you want. And this is really going to benefit walls with higher axial loads because you will then get a higher number than you would get from this table. So impact of this is similar to Chapter 11. We will need to expect more walls to require strengthening in higher seismicities. So wall force redistribution. So a little background, there are 4 failure modes that are checked in Chapter 11 for wall piers. 2 are deformation controlled modes, rocking and bed joint sliding, and 2 are force controlled modes, so toe crushing and diagonal tension. So we have this kind of mix and match of some deformation controlled, some force controlled. That's not so bad when they are in separate lines, especially separated by flexible diaphragms. But the linear methods don't specify how to evaluate multiple modes in a line of resistance. So typically we look at each individual component when we're doing ASCE 41 and evaluate it separately. This is also true of concrete piers in ASCE 41. So there's no provisions to allow moment redistribution between wall piers in the same line. However, Chapter 16, the special procedure, does classify the wall piers in the line based on their behavior in relation to each other. So for example, if you've got rocking control piers in a line with shear controlled, you actually ignore them and distribute the load to the shear controlled walls. There's a whole flow chart that you can find for this special procedure on even how to negotiate this when you end up with mixed modes in the line. But what it does is allow the engineer to better utilize the total strength of a line of resistance. Just because you have one wall fail in that line doesn't mean that everything needs to get strengthened. So we wanted to come up with some method that would allow for some moment redistribution if possible. So we can better utilize that total line strength, and nonlinear studies have indicated that yes, once you get yielding in one component line, it starts to redistribute. In concrete, you can redistribute up to 20% if you've got ductile members. And the New Zealand URM code actually allows for up to 50% redistribution. So we studied what level and how could we implement this. So we did different technical studies. Here's an example of where moment redistribution could potentially be possible if you've got mixed modes. This case just included deformation controlled modes. We started with that. And you can see here the 2 end piers are rocking controlled. That's our little R there. And the 2 interior ones were governed by bed joint sliding. So that's the little BS and, over on those 2 interior ones. All these walls have the same stiffness and they have the same demands. So they're all 12 kip demands. The capacities are slightly different because there's a little less gravity load on the two end piers. So that's why they ended up being rocking controlled instead of the bed joint sliding. And these two end piers with the rocking are just shy of the capacity to work. So we've got 11 kips versus 12. Whereas the interior ones have extra capacity. 15 kips is their capacity versus 12 kips. So it seems like we're really close to making this wall work. But technically the provisions would say it fails. The two rocking piers would need to be strengthened. We also looked at what happens if you mixed deformation controlled and force controlled elements in the same line. So if you have rocking and sliding, but you also add in diagonal tension, which is force controlled. The catch is that these force controlled elements are much more brittle behavior. So it's not going to be the ductile modes that we're hoping for. So we ended up, after looking at all of this, determining it's not really acceptable to permit redistribution once you get force control mixed in. This is consistent with the New Zealand code, which only allows it if the wall piers are, all the piers are deformation controlled. In addition, 4117 requires that rocking wall piers be neglected in lines of resistance that are all deformation controlled. So this bottom figure shows that with that, so you've got this one force controlled, you then have to ignore these two rocking controlled piers. Their demands would go down to 0, and that demand would be redistributed to the two interior piers, at which point your interior piers are so much worse, the redistribution wouldn't even be possible in that case. So after looking at all the different factors involved in this, we ended up determining that not allow redistribution in areas with mixed deformation and force control modes. We did do a case study on an actual existing building in a high seismic region that had been through earthquakes, that has had a lot of studying done on it. And so the wall piers were all based on actual realistic conditions. And we calculated outcomes for chapter 16, which has that kind of iterative procedure, as you can see here, for determining whether you're deformation controlled or force controlled, and what do you do about it. And we also looked at it for chapter 11 to kind of see, okay, we've already got this special procedure that allows some redistribution. What happens when we compare that to chapter 11? And in one case study, we had first floor wall piers that were all force controlled under chapter 11 due to the high axial load ratios. The second floor all ended up being deformation controlled. And you can see here at the second floor, the blue is the special procedure and the red is chapter 11. We're actually getting fairly similar results going across, at least on an average basis. If we have the mixed force and deformation controls here at the first level, now all of a sudden our two procedures start to diverge quite a bit. Chapter 16 provisions don't even consider that, full force controlled, all the piers were rocking controlled. So you got a very different result. And it actually shows that everything worked. Whereas then when we went to chapter 11, the first four wall piers were all overstressed, were almost all overstressed. And even on an average basis, we're all overstressed. So again, based on this, we were looking at, really, we shouldn't be allowing redistribution when we have mixed force and deformation control wall modes in the same line, because there's just too much uncertainty. The different methods just aren't quite agreeing on that. We did a second case study with the same wall. The thing that was actually varied was we used a higher F prime over M value. So basically we said the masonry was a little better. And when we did that, then these piers on the first floor became deformation controlled. That's how slight a change can sometimes switch you between these different modes. So even under chapter 11, it was deformation controlled. And the acceptance ratios we got here then ranged from, about 0.4 to 0.8. And the average actually came in and was all the same as the special procedure. So we were getting similar outcomes between Chapter 11 and 16 when it's all deformation controlled and the force controlled methods aren't applicable. And since the Chapter 16 allows this aggregate approach and more effectively uses all the wall piers compared to 11, that's evaluating each single one independently, we figured that, again, that we shouldn't just have one wall pier dominating all of the behavior along this line. They're really going to work together. There's going to be some softening, and we can allow for the redistribution of forces to the adjacent walls. So going back to that original example wall, if we do redistribute forces, we actually only needed, 2 kips to be moved, going from 12 to 10 here. So if we take that 2 kips and moved it over to the adjacent walls on both ends, it was only a 17% redistribution. And then the final acceptance ratios all became under 1, as opposed to our initial ones that were just slightly over 1. Yet we didn't decrease the total force in the wall line. So again, this points to the indication that this is an acceptable procedure. We're getting behavior we expect. So that's going to be our recommendation to the ASCE 41 committee. Maximum of 20% redistribution for collapse prevention was chosen. Is it similar to concrete and ACI? We thought the New Zealand allowance of 50% was probably a bit much. And then a 15% redistribution allowed for life safety, and no redistribution for immediate occupancy, because we really want to prevent that softening, because we want to make sure there's no cracks and that the building is still able to be used after an earthquake. We did include additional limitations, that the walls have to be in the same line of resistance and they have to be considered primary components. This is because secondary components are already given a break if they're deformation controlled. In addition, diaphragms and collectors must be evaluated to transfer the redistributed forces. So if you've got a spandrel that's going across the wall and joining the tops of the walls, like we had in our examples, you would then go in and check to make sure it can actually carry that 2 kips, say in that example, over to the other masonry wall pier. There has to be some method of transferring the load. Last recommendation that we had to make was on URM rocking axial stress in Chapter 11. So the M factor for the linear procedures for rocking has a footnote. You always have to look at footnotes and codes. And this footnote limits the axial load ratio, FA over F prime M, to less than or equal to 4%. This is because the acceptance criteria were originally calibrated for this maximum axial load ratio. However, the committee and ASCE 41 have gotten user feedback that this is limiting. A lot of times you might have a ratio that's just 5% or 6%. Do we really have to jump from treating our wall as force controlled with an M factor, or sorry, deformation controlled with an M factor, and bump it down to force controlled when we're just slightly over this limit? So we went back and re-examined the original test data used to develop the M factors in 4117. The M factors do decrease as the axial load increases. And you can see here for a squat pier with a height, effective height over its length of less than 0.5 down here, the M factor at 4% goes from 3 down to 1.5. For a slender pier, if your height over H over L is greater than 1.3, at the 4%, it was 8, but then as you head down to the 8% axial load, you're getting an M factor now of 3. And then the square pier kind of in between is showing a change down from 6 to 3. So this slender pier is actually dropping much more dramatic, much faster down in M factors as you go up in your axial load ratios. And then beyond 8% axial load ratio, what you end up with is your M factors all drop, 1.5 or below, and you're really not getting ductile behavior anymore. So we really still think that there does need to be an axial load ratio limit, but we can extend it from what we have now. So the proposed revision is that the footnote will be revised and M factors will be allowed for axial ratios up to 8%. Now at that 8% level, you'll have to take half of the tabulated value, not to exceed 3.0. So that's capturing the behavior of the squat, the square, and the slender walls that we were showing in that graph. And that interpolation between the 4% axial load ratio and the 8% will be allowed. And then beyond 8%, we'll still consider it force controlled because you just don't have the ductility anymore that we expect out of a member. So the impact of this change is a wider range of wall piers now may be considered deformation controlled. You will get some lower M factors as you go up in those axial loads. And the nice thing about this change is we're actually reducing some of the conservatism that was present in 4117. So we're opening this up a little bit more. So this wraps up the proposed changes by the ATC 140 project for unreinforced masonry. I really want to thank you all for tuning in today. As mentioned, additional webinars are planned for background changes on concrete structural walls that'll be coming up. And I'd love to hear any questions you now have on the unreinforced masonry material.
Thank you, Rebecca. We do have some good questions for you. I appreciate very much your presentation, giving us the details on how the FEMA P-2208 document addresses the items that we care about for URM. Before we jump into our question and answer period, there's a couple of things I'd like to just summarize. For those of you who are eager to receive your PDH certificate, note that they're only provided for those who registered and participated in the live webinar, not watching the recording. You can expect your certificate within 4 weeks due to the large volume of participants. So something more than 800 participants. Please understand that we can't make exceptions to the PDH policy. If you have a question that you haven't yet submitted, please type those questions into the Q&A window in Zoom now. We may not have time to answer all of the questions. We've got quite a few teed up that folks typed in as they were hearing the presentation. We'll get to as many as we can now, and then as many as feasible after that by email. So with that, I'm going to jump to a couple of the questions that we've received so far, Rebecca, so that we can get started on some Q&A. For the ones that were sent in advance, sent in as we were discussing, I've grouped them into some categories. So we'll start with something that's about existing conditions, then some performance, some retrofit and analysis items, and if we get to it, maybe something on testing. Mm-hmm. So on the existing conditions, the question is, in modeling existing unreinforced masonry structure for seismic vulnerability assessment, how should the deterioration level be quantified and taken into account?
Great question. So all of these studies, of course, were all focused in on linear analysis for the most part. And with the linear analysis, you use basically the recommendations in ASCE 41, which I believe kicks you back to TMS for your wall stiffnesses. And that is what you would then use. Sometimes we also often look at deformations and say, well, we know we're going to have some softening, and we might occasionally in our office bound it with 2 if we're actually going down the full linear analysis modeling path. But if you're just doing a 2D analysis, yeah, you can just follow the 41 guidelines that then kick you over into TMS for your wall stiffnesses.
Okay, thank you. Let me go to the next one. Have you considered the Secretary of the Interior standards for treatment of historic buildings, in case that's what you fall into when you've got this URM? Any words to the wise there?
Yes. So we often do, we often are looking at buildings where we are remodeling them, often using historic tax credits, which then fall under the NPS, the National Park Service, and the requirements, or if we are operating within a landmark building. And we do often have to educate sometimes the engineers back east on, yes, we really do need to add, say, a brace frame into a building for safety reasons. But a lot of what we are doing is often, can you very selectively go in and do a retrofit from different conditions? You know, maybe you're going in from above a floor so that you don't disturb a historic ceiling, or you're coming in from below because you've got a historic wood floor that you're trying to save. We have to be very selective in what we're doing, but we still want to provide seismic safety. And it's not just seismic safety too. You are also, by doing this, making sure that the building is still potentially there after an earthquake, especially, you know, say a smaller earthquake, and making sure that the NPS understands that this also is preserving our history for the future in case, you know, an earthquake comes along. We don't want to lose this history. So a lot of different ways to deal with it, and sometimes it you know, there's a little give and take with them on what we do and where we do it. But we do try to advocate for seismic safety in these buildings.
Okay, great. That might relate to the idea of the magnitude of the earthquake. Is there any way to use the URM special procedure to satisfy the basic performance objective?
So through the document right now, most areas that I've dealt with reference the International Existing Building Code, which does allow ASCE 41. And when you're in ASCE 41, it does say the special procedure is a limited safety objective and doesn't meet that basic safety objective. However, sometimes people stay within the International Existing Building Code, which has an appendix. And if your jurisdiction has adopted appendix, I think it's A1, but I could be wrong. It has something very similar to the special procedure that some jurisdictions will allow. So it will really depend on your jurisdiction.
Okay. Are there any recommendations for the effect of retrofit elements on existing foundations?
Yes. So if you are putting your retrofit element onto an existing foundation, you would still need to evaluate that existing foundation. And you do that evaluation using the chapter 10, the concrete chapter, and run through there. If you're looking at the concrete piece, or if you are looking at the soil underneath, then you'd be going to the chapter 8 and looking at the foundation for the new forces that you put onto that foundation.
Okay, thank you. On slide 20, you talked about drift limits. Do the drift limits apply to the vertical elements of the lateral system or also to the diaphragms?
Those drift limits that we are recommending are for the new vertical elements. So they're just for the vertical pieces, you know, your new brace frames, concrete shear walls. They are not for the diaphragms. For the diaphragms, you would still use the special procedure chart, that lovely one that allows for much larger DCRs than you would usually get in the regular procedures.
Okay, great, thank you. One asks, what about fire cuts at the connection to the wall?
Oh, I'm assuming they're talking about how joists are often embedded in the wall, but have a diagonal cut on the end. This is to allow, so if there's a fire, they can kind of rotate out and not take the wall down. So this document, ASCE 41, is just checking seismic loads. It's not checking gravity loads. So if you have a concern for some reason on gravity loads, you know, you would need to address that. Anything you are doing for seismic, say anchoring your wall to your joists, you just want to make sure that when you are applying that anchorage to the joist, you're not too close to the end of the joist. You'd still need to maintain the NDS values for, looking at like bolt tear out towards the end of the joist. So you'd have to take into account that fire cut edge.
Okay, thank you. Moving on to some sort of retrofit and analysis related questions. Early in your presentation, you showed the diaphragm response when a moment frame is added midway along the building, and the behavior now looks like two side-by-side sad faces, right? One diaphragm acting like two diaphragms. Is the intent that the diaphragm flooring be cut at the location of the moment frame to make it two independent diaphragms, or do you simply make an assumption without altering the flooring?
So I'm trying to find that picture. I'm not seeing it, but I know which one you're talking about.
I do recall when you had a midline and we had sort of two.
Yeah.
Let's see if I can find it.
There it is. This guy maybe.
Yes.
So yeah, this the intent is not to cut the diaphragm. You would add your element, you'd attach the diaphragm. This diaphragm was behaving very flexibly, or had been modeled very flexible. And so that is why you end up with this behavior rather than something that might look a little more like it was continuous. But I wouldn't advocate for cutting a diaphragm.
Okay. The next one has to do with applying shotcrete to URM walls. And I have a couple of questions on that line. I'll try to get the big idea here. So if you've got an existing squat URM wall, it's strengthened in plane by adding shotcrete to one side. What's the effect on the 4 URM failure modes? So rocking, bed joint, sliding, toe crushing, diagonal tension. How do you add the capacity of the URM in the shotcrete? And does adding the shotcrete change the failure modes that you need to be considering?
That is a great question. Unfortunately, the document doesn't really address that and what happens when you've added it, neither in the main body or in the special procedure. Typically, what we usually see is people will distribute the forces based on stiffness. A lot of your force will go to your new concrete wall. You'll have your force that goes to your URM wall, and then you'll just use the same mode that you had before.
Okay.
If you could find a technical justification or did some additional, nonlinear modeling, maybe you could come up with something, you could justify through engineering methods something different. But that's at least the first step usually in the process.
Okay, thank you. A couple of folks asked about the program used for 2D or 3D analysis.
Yeah, the 2D, I believe, was done in RISA. The 3D program, I do not know which one they used. I can look that up and get back to it and send that out with the responses. I wasn't the one performing that particular study, so I don't know offhand.
Okay, great. It'll be in the written questions that are submitted. So thanks. How do we obtain curves for force displacement for concrete elements in ASCE 4117? They're asking. So this is like if you're going to do a retrofit using concrete elements.
You would go to chapter 10, and they believe they also have some recommendations in there. Certainly for nonlinear, they've got all of the information.
Okay, so it's you're using elements. The elements that you add, you're satisfying chapters other than chapter 16. Chapter 16 is limited to the URM portion of the behavior.
Yes, it's just limited to URM, to what you expect of the new elements that are going in there, but you still might have to go a little bit outside just to get some of these basic things, just like you would step to ACI 318 for your concrete capacities.
Okay. Your example talked about using reinforced concrete walls for new vertical elements. They asked, can you clarify if reinforced masonry walls can be used for the retrofit?
Yes, you could use reinforced masonry walls. We didn't study that particular one, but there wouldn't necessarily be anything stopping you. I guess that's usually more of a constructability method we've found. For one thing, we usually like to tie the masonry element to the concrete, so we get a little out of plane help on the masonry wall. And you can go in and you can shotcrete with concrete, so you don't have to try and build within such a tight space. I can see trying to add the rebar might be a little difficult in adding a reinforced masonry rail right against a new one. If it's at the mid-span, it'd be easy.
Sure. A similar question, are there provisions for using FRP to retrofit?
There are no provisions in ASCE 41 for that. Doesn't mean you can't use FRP, but you would then need to use another document like the ACI guide on FRP or manufacturer's studies. And you'd have to potentially get buy-off from your building department.
Okay. Let me see. Still, I'm going to go jump back to one that came in about, say, performance issues and drift limits. They say with respect to the open front building with moment frames, maybe slide 21, the moment frame columns and beams often get prohibitively large when meeting the 0.75% drift limit, especially for structures with tall ground floors. If there's no brick at that lower level grid line and weak soft story concerns are addressed, could that drift limit be relaxed?
Yes, so basically you're saying, especially if you have a very open front building that didn't even have any masonry up above, and you wanted to deal with that open face, we had still kept the 0.75 because there were also concerns about even these masonry walls that are perpendicular, how much they are then shifting out of plane. Especially by the time you get to the midspan, it means that your midspan, you've got not only the deflection of the frame plus the deflection of the diaphragm. So there were concerns there. That's why we had left in the 0.75% limit. But if you had reasonable engineering justification and the building department buy off, that could be an option, especially if you're going for a limited performance objective.
Okay.
We have done that for things like more of a bolts plus, something where you're just fixing the worst things on the building. It's much better to get a moment frame that will at least take all the forces, even if it doesn't limit drift for a limited performance objective.
Great. So project-specific approaches. Thank you. Let's see. Does the document mention what types of retrofit would alter the behavior of the URM to deformation controlled or force controlled? So maybe so you can change the mode of response.
Neither ASCE 41 nor FEMA 2208 addresses that. We weren't studying what led to a change between the different modes. I know from experience, if you play around with the equations, you can start to see that different things like axial load. Axial load is actually a big driver for rocking, and some of the other modes can make a difference. So that's more practice-based rather than anything that's addressed specifically in a document.
Okay. If a designer relies on cross walls in their evaluation, are there any provisions for considering the case that cross walls may be mistakenly identified as non-structural and are removed by future occupants?
Yeah, it's always a slight danger that somebody might come in through and take out the interior walls. When we have actually done a retrofit, you can state in what your lateral system is. I know we have a spot in our documents where we might say the lateral system is the unreinforced masonry walls and interior cross walls, so that there's a hint at least to a future engineer. But you can't actively prohibit people from doing things to a building. I mean, somebody could take out a structural wall that's very intentional. There's only so much you can do as an engineer. At some point, the building owner needs to ask questions before doing work.
Yes. Are there any horizontal restrictions when considering the vertical elements needed on the same line?
Are there any, what kind of restrictions?
Horizontal restrictions when considering vertical elements to be on the same line. So rules about what qualifies as a line of resistance if they're not perfectly aligned, let's say.
Oh, if they're not perfectly aligned. No, there's no rules on that. Typically, we've just exercised engineering judgment on that. So if you've got a slight step in a masonry wall because they wanted a little 1-foot jog to make it look nice, that's might be something you just consider as the same line. And at some point there's going to be a limit, but we usually leave that to engineering judgment.
Okay. So this question gets back a little bit to mixed modes. Since mixed deformation and force controlled modes of failure are present in the same building, do you also arrange the connections of components like added vertical elements to be mixed somehow, rigid, semi-rigid, and flexible, if the demand for limited drift is met? Is this permitted by general provisions and by the special provision?
So you're looking at, sorry, I just want to get to one of the mixed mode slides just to illustrate. So you were saying if there's mixed modes.
They're asking if you can, arrange some added vertical components based on those mixed modes of response, that you kind of tune the added components based on the modes of response that you're addressing.
Yeah, so if you just wanted to fix certain piers, but maybe not others, to try and, not have this particular force controlled mode. Yes, you can. You do have to be very careful, I think, with linear procedures, because sometimes the linear procedures don't always capture exactly what might happen as, say, these, force controlled walls that have a lot of load start to soften and then start to change their mode and behavior. So it can be a little difficult to predict, but certainly, we have gone in before and said, okay, we're going to strengthen up this section and reduce forces, and maybe that will also then potentially, kind of reduce what's going on in with these different modes.
Okay, good. I think we'll just take time for maybe 2 more I've got here. This one is a different subject than we've been asking questions about. It gets to the H/T ratios that you discussed in detail. How did you assess the H/T ratios for different spectral accelerations? Can you explain the methodology a little more? This is the Elwood and Penner.
Yes.
Work, right?
So Penner and Elwood had done physical testing on a small number of actual URM walls with different parameters. And from that, they then developed computer models of the walls, making sure that they matched with their results. And then they ran parametric studies on that. They ran something like 20,000 computer models on different walls with different spectral accelerations and everything from that small subset of physical tests. And then they developed their equations. And so that's where we then came up with information on what that equation was that follows. So you get different spectral, you can determine what H/T is reasonable for different spectral accelerations. But that all came out of their work, and they were up at the University of British Columbia, UBC at the time. And those papers are available too, if anybody wants to study them. We can maybe send some of that out with the questions and answers in case anybody's interested in diving into it.
Okay, great. One last question then. The required testing can be too expensive and invasive for routine seismic evaluations. Do you have any suggestions to manage those expenses?
Yes, that if you follow all of the ASCE 41 recommendations, you do have to get quite a number of tests per masonry wall line for your shear tests. It can be expensive. We often look at what the different masonry classes are and try to do subgroups. Sometimes we've also negotiated with the building department to say, can we do every other floor, especially if you've got like a 6-story building, not to have to do so many tests all the way around, especially if it's got interior walls. So sometimes we are able to negotiate down and say, this is a reasonable number, especially if we've walked and can see those walls and can see that They have very similar appearance, and you scrape the joints and you find, okay, they all tend to behave in a similar way. That can lead to a better feel for, yes, this reduced testing might be acceptable.
Excellent. Thank you, Rebecca. We'll end the questions and answers there. We thank you again for your excellent presentation. We got to almost every question that was asked, and we'll have just a few things left when we report to folks. So just a few closing words from the Applied Technology Council. Please be sure to click the survey link that pops up when you leave. We especially appreciate your input on topics that you'd like to see covered in future FEMA NEHRP webinars. That's what we use in order to plan our webinar program. And you can expect a follow-up email in the coming days with links to the recording, the handouts, and the survey again. We had a few people asking questions about that, and so you will receive links to the report, FEMA P-2208 report, the handouts, which are the slide presentation, and the recording will be available. I'll reiterate what Rebecca said earlier, that the recording for the earlier nonlinear analysis webinar based on FEMA 2208, that is also available already on the ATC events page. And the announcement for the concrete walls webinar that will be on December 11th is also on the ATC events page. And there will be an e-blast that goes out on that in the next couple of weeks. On behalf of FEMA and the Applied Technology Council, I'd like to thank Rebecca for this presentation, and thank you to everyone for joining us today. This concludes the webinar.